what is this equal to? Okay, again you do the same trick. You put an A over here. Okay? And then you put an A over here and put an A over there. Because you put an A over there, you have to put a 1 over A outside. Okay? Now you do a change of variable. A of t minus t naught is equal to t prime. Then you will have the fact t naught is constant, so you have a dt, which is actually the same as dAt, is equal to dt prime. Okay, so this is just dt prime. Okay, so this should be equal to 1 over a f of 1 over a TA. If you take this equation, TA is just equal to AT is equal to t prime plus t naught. Let me see, am I correct? T prime plus AT. Okay, AT is just equal to t prime plus AT naught. So I can write this as 1 over a times AT. AT is just equal to t prime plus AT naught. Okay, and then this one just becomes delta t prime, and then dt prime. Okay, and what do you get when you evaluate this integral now? You set t prime to 0, right? It's not f of t naught. It's f of something else. So by the definition of this shifting property of the delta function, when you have function multiplied by delta function, you just pick out the value of this function at t prime equal to 0. What is the value of this function at t prime equal to 0? Yes, Nancy, what do you think it should be? What about Liu Qing? What? Yes, very good. T naught. Okay, T naught. You set t prime equal to 0, you get T naught here, right? So what you notice here is that if you have this function being scaled, it behaves like 1 over a delta t minus t naught. Okay, it just behaves like that function. Okay, this is the scaling property of a delta function. Are there any questions regarding what the delta function is? What happens if you were to differentiate the delta function? If you were to differentiate, what do you get? Well, it's hard to imagine what you get when you differentiate the delta function because it's not actually a function. It's a distribution. It's a limiting case of something that looks like that. Okay? And a unit step function was difficult enough to differentiate, to find its derivative of. So what do? You relax it. You find an approximate version of this. And then differentiate this. And you take the limit and then you figure out how to differentiate this. So if you want to differentiate this function, find its derivative, you'll be pulling out your hair, right? Because you don't know how to do it, because it's not a function. So you go back to this thing. Again, it's not a function because it's not well defined at the two ages. Okay? If you don't feel comfortable about this, find an approximation to this function. If you feel comfortable about this, that's fine. You can say that this is just like two unit step functions, right? If I take the derivative of this, what do I get? I get delta function on the left, and then on the downside, what do I get? I get a negative delta function. Okay? So if I were to take the derivative of a approximate delta function, let me call this the approximate delta function. If I were to take its derivative, I will get a delta function on the left-hand side okay, which is the 1 over delta, the height of this thing, times delta t, right? And then on the falling side, on the downside, the downfalling side, I should get the negative delta function. Okay, so it should be minus. Also, the height of this thing is quite high, so it should be 1 over delta. But this delta function now is positioned at this point. Okay, can you see that? The approximate delta function when differentiated gives you two delta functions side by side. Okay, two delta functions side by side. And what do you think? This is just the approximation to the derivative of a delta function. And then the limit when you make delta very small. So you get something like this together with a function that looks like that. Space delta apart. That is the pictorial diagram of this function. Okay? And when you make delta very, very small, it gives you two impulses that are very close to each other. That's called a doublet. Okay, this is becoming the derivative of the delta function, which is called a doublet. Okay. So pictorially, can you see this in your mind? What a doublet is? Yes? You could, but mathematicians are going to get very unhappy with it.
They're already unhappy.
Mine as well. This way, would you get a summation of the delta functions at some point?
Okay.
And then that evaluates.
Yeah, then this function becomes more and more ill-defined. Okay, you can always think of it as a limiting case of two functions. Okay, so the doublet is the derivative of the delta function. You can think of it as two impulses just next to each other. So a limiting case of a signal that looks something like this. In the real world, you never make an impulse because it's hard to make. It's quite easy to make a pulse that looks like this. It's called doublet. Okay. So this is what you can do in the real world. This is what you can do in your course. Okay, just make two arrows like that. It's very easy to do. So what is the property of a doublet? Let's look at this as to when you multiply a function with a doublet and integrate, what do you get? The first thing I should get is to apply the integration by parts rule. Okay, because I see an exact derivative over here. So I do integration by parts. Then what I get is that I get integration of this thing, which gives me that thing, times f of t minus infinity to infinity. That's the first part I do when I do integration by parts. And then the second part is actually minus infinity to infinity delta t. And then the derivative of this. Okay, that is the integration by parts rule. If you remember your integration by parts, I derived this rule once before, right? Or you want me to derive it again? Otherwise, you have to commit this to memory. It's too slow to derive in class or in an exam. Okay? So, the first term, what does it evaluate to? The delta function is always 0 outside space. No, it doesn't evaluate the f of 0. At t equal to infinity, what happens to this function? 0, right? At t is equal to minus infinity, this is again 0. Okay? So at the two endpoints, the first part is always equal to 0. Did you get it? Because this function looks like this. So it's always 0 outside the origin. The second function, you can use the shifting property or the sampling property of the delta function. And what does it evaluate to? Evaluate to this function evaluated at t is equal to 0. dt at t is equal to 0 with a minus sign. Okay, this can be also written as f prime of 0 with a minus sign. So the property of a delta function is that when you multiply it by another function and integrate, it always gives you the derivative of the function. What is that? This one I do integration by parts, so integrated I get rid of the prime. Okay, but then integration by parts, I keep this as what I have integrated, and then differentiate the other part, and then integrate. Okay, that is the integration by parts rule. Okay, I think I have it for the day now, so I think I can let you go.